Please welcome Vice President and GM, Ben Sell.
All right, welcome everyone. Good afternoon, and really glad to be here. I've been at Intel for 22 years working on leading edge technology, and I'm really looking forward to share some of the details of our process technology innovations with you. After that, my colleague Myung-Hee will provide details of the exciting and revolutionary work that's being done in the technology research, followed by work that she and her team is doing on system technology co-optimization and 3D integrated circuit. As Naga and Kevin have shown this morning, we have been focused on execution and extending our roadmap to make sure we can meet the needs of our customers. Intel 18A is in risk production and will be in volume production later this year. Intel 18AP provides significant improvement over Intel 18AP, as you have heard this morning, and we expect this to be in volume production by end of next year. New to the roadmap is Intel 18APT, a node that is designed as a bottom die for 3D integrated circuits. 14A, 14AE will give a full node worth scaling for both area and performance, and is expected to go into risk production in 2027. So let's dive into the details. Intel 18A is the first technology combining two revolutionary approaches, RibbonFET and PowerVia. RibbonFET is a gate-all-around transistor improving the electrostatics of the device, which helps improving performance, especially at low voltage operation. The inset you see here is the picture of the 4 tightly stacked ribbons that we have in production right now. PowerVia is our approach for backside power delivery. We are moving the front side power routing to the backside of the wafer, providing 3 critical benefits. First, we reduce the voltage droop from the bump to the transistor, giving performance enhancement. Second, we can relax the lower layer metal pitches since we don't have to make room for power routing anymore. And third, it allows us to improve our library cell utilization on a typical design, giving additional area scaling. The inset you see in that picture is what we're actually running in production today. To me, obviously, it's a beautiful picture where you see front-end interconnects, transistors in the middle, and backside interconnects very tightly integrated. More importantly, this delivers the promise that we started with on our products. We previously published enhancements that we measured on our test chips on this design. We now see the same enhancements on our lead products on Intel 18A. And this gives us more than 15% performance benefit at the same power at low voltage, and even more benefit at higher voltage. So the combination of PowerVia and RibbonFET gives us good performance enhancement at both low and high voltage. In addition, we're getting a 1.3x chip density improvement over Intel 3, providing us a full node benefit with Intel 18A. In addition to logic performance, we also put a lot of focus on improving our SRAMM functionality and area scaling to make this competitive compared to industry offerings. On the left-hand side, you see a 256 megabit high current cell SRAM without assist, meeting the industry standard spec for SRAM without assist. We're also providing assist functions where we reduce the spec by another 70 millivolt and also meeting that requirement. On the right-hand side, you see the high-density cell on SRAM, which is about 8 to 9% smaller in area, with assist also meeting that same requirement. So overall, we're offering a very competitive SRAM option for Intel 18AP and 18A. We have made very good progress on our intrinsic transistor performance. The process we currently have in risk production is at 90 to 95% of our target. As you can see on the left-hand side, the blue data points are typical wafers that we run in the fab. The gray points are our targets. We have identified the right process options to get us to 100% of our commit. As you can see on the right-hand side, there are a few more tweaks we need to do on the process to get all the leakage targets, but this is the process that we'll have for Q4 25 production. So, is backside power delivery expensive? And the answer is, it really depends on how you do this. The left-hand side shows what the lower layer metal cost is for a standard front-side flow. For this generation, if you have front-side power delivery, you need metal pitches less than 25 nanometer, which requires multi-pass processing for both the metals and the vias. If you then add backside power delivery, you add a backside contact flow, you add backside metals, this is just a straight cost adder. However, if you plan for backside power from the beginning, you can relax the lower metal layer pitches. And in the case of Intel 18A, we relaxed it to 32 nanometer or above. And this enables us to do direct print patterning, very simple short flow for the lower front-side metal layers, which is not just a short and simpler flow, it's also significantly less expensive. So this flow almost offsets all the costs that we add for the backside power delivery cost. So the right-hand side is what we're doing in 18A in terms of offsetting the cost of backside power delivery. Our yields are progressing well, and we do expect to be HVM level yields in Q4 this year. The best wafers that we produce are typically a good leading edge indicator in terms of where the yield is going to be in the upcoming quarters for median yield. The best wafers we have produced, indicated by the wafer on the chart, are already meeting the HVM defect densities that we need to do on average by end of this year. Overall, this yield is equal or better yield than the yield we had for all the leading edge Intel technologies in the last 15 years, even including 22 nanometer. So with this one, we are in risk production, and we are ready to ramp the process in the second half of this year. As we talked this morning, Intel 18AP is a significant enhancement over Intel 18A. We worked a lot with our customers to understand what features were missing on Intel 18A that the customers really want to see to apply these technologies for a broader range of markets. We added VT types, we improved the intrinsic transistor performance, and we tightened the skew corner. In addition, we also added smaller ribbon sizes, as you can see on the left-hand side here, that allows our customers to further optimize for reduced power. We already have 2 products of Intel 18AP running in the factory and taped in. Overall, this enables us to get about 8% performance per watt increase at matched chip density. The new addition to our roadmap is Intel 18A PT. This is the industry's first base die with backside power delivery, enabling both top and bottom connections. We started this journey with Intel 3T, which is our first volume-based bottom die. And compared to Intel 3T, we are getting 20 to 25% compute density increase, 25 to 35% power reduction, and about a 9x die-to-die bandwidth density increase. This is really designed for data center, edge AI, and XPU applications. And we're building this on the learning that we got from Intel 3T, which enters risk production later this year. We have two different TSVs on this process, one optimized for signal and one optimized for power to get the most out of this technology. And all the design rules and the models are compatible with Intel 18AP for ease of use in terms of being able to transfer IP easily from Intel 18AP to Intel 18A PT. I'm really proud of what the team has done on Intel 14A family. We have worked very closely with all our customers and ecosystem partners to understand what we need to do better compared to 18A, and what we can learn, and what are the features we need to add to really address a wide range of market. We offer a wide VT range, and we offer 3 different libraries: a tall library optimized for frequency sensitive applications, a mid-sized library for performance per watt applications, and a short library for area and power sensitive applications. This is the second generation for our 2 big innovation. The second generation for power via, which we call Power Direct, and the second generation for ribbon fed, which we call ribbon fed 2. And it makes use of HighA EUV to simplify the process flow and reduce cost. Overall, we're getting 15 to 20% performance per watt increase over Intel 18A and 1.3x chip density, providing us a full node worth of scaling. To make sure we get the full benefit out of the shorter library, we are introducing turbo cells. These are cells that are specific for designs where you have double height libraries and want to really optimize the transistors with those double height libraries to make sure you can provide very high drive current in an area efficient way. As you can see here, we have options where we just increase the ribbon widths within this double height library, or where we even merge the ribbons to provide very wide ribbons. And we have options where you can do it symmetrically, giving us both for N and P, and where you can just choose N or P to improve this. Overall, we are working very closely with our EDA partners to get the most benefit out of these cells and make them easy to use. Finally, I want to talk about HighA EUV. Why do we do this? It's very simple. It's lower cost. In the middle picture, you see a pattern that has been generated by a single pass HighA EUV at a pitch that is comparable to the pitch that we need for 14A. The right-hand side shows a very similar pattern generated with the traditional approach, where we use 3 EUV exposures and overall about 40 process steps to generate this pattern. So overall, we see much shorter, simpler flow, and this is the type of application where we use HighA in 14A, which reduces the cost compared to the multipass 0.33 HighA EUV. Additionally, this provides the option to depopulate metal layers and get additional performance enhancement. So now we want to talk about the innovation across technology building blocks. And for this, I would like to ask the next speaker, Myung-Hee to the stage.
Good afternoon. Thank you, Ben. Today, I want to talk to you a little bit about innovation through technology building blocks. 2 categories, silicon and packaging. Before we dive in, let me talk to you a little bit about how the flow goes. First, extension. The second, disruption. third breakthrough. What do I mean by that? Extension, we need to extend current ecosystem as much as we could to get the ROI of technology benefit. Disruption, we need to disrupt current ecosystem for us to change for moving forward next generation. Breakthrough, it requires complete different paradigm shift. And that's the three areas that we are working on Intel Foundry. I'd like to share a little bit about the view of that. Extension of the silicon. Silicon, we have been known very well. Two parts of the silicon very important. One is transistor, either scaling of performance, power area, or back-end interconnect. RC has been really a biggest issue in our industry. So I think that two areas are main topics of the silicon. For our mission, Intel Foundry is extreme scaling to get the best benefit out of the scaling to provide value proposition for AI compute where we are going. Extension, we demonstrated up to 6 nanometers of gate length, which is about 2 to 3 times shorter than gate length of the ribbon fat. This is actually opening up the doors. The ribbon fat can actually go for further area scaling. The next is actually going to be the disruption. CFET is known in industry. What it is truly a 3D CMOS. Not anymore in the packaging word terminology. It's actually coming into the transistor. We are stacking N, we are stacking P together. We have demonstrated functional devices, good performance, and we are continuing to scale further in the next generation to get the area benefit. Ultimate area efficiency in CFET is promising with the performance. That's where we are heading. As we actually make a transistor smaller and smaller, one of the problems is that we are, in the given chip size, we're packing more and more transistors. Back-end RC penalty has been really biggest issue, and we innovate through the alternate integration method using the metal etch and using the alternate metals like ruthenium and incorporating air gap. We further go beyond of the RC scaling. So we are going in this journey in the disruption, breakthrough. For us, silicon is bread and butter. Silicon ecosystem is so robust, it serves us really, really well. But as device becomes really, really tiny, the silicon has a fundamental challenges. We need to look for new materials. What do we know in our industry? We know changing material takes time. It requires a really long lead time. For us, the start need to do now. We need to start now to look forward what we need to do for next generation of the beyond the silicon. So we demonstrate moly disulfide with the 2D materials, ultra thin bodies, and ultra performance. So we are going in this journey. This journey, both disruption and breakthrough, we will need the ecosystem together with us because this is a disruption and breakthrough. We cannot do it alone. And I'm really looking forward to working with all of our ecosystem partners in the R&D space. Next, packaging. Why am I talking about packaging? Because for me, packaging is not just a packing together of the chips. It's actually a differentiation. We have opportunity to create a technology differentiation through the packaging. Extension is going to be sustainable device transfer with infrared laser debonding techniques. So we actually can do environment safe and environment friendly transfer to introduce differentiation devices. Disruption is a selective layer transfer. Imagine chip to wafer flexibility. Your top die doesn't have to be same size as a bottom die. That flexibility with the wafer to wafer bonding throughput. And ultra thin die chiplet enabled. Can you imagine what you can do in the 3D space? And that's the era we are looking into in the disruption space. Third, let's change the paradigm. Current chip-to-wafer hybrid bonding is really enormously progressing. However, we have a lot of challenges. Changing the paradigm with self-aligned fluid action hybrid bonding techniques, we can actually do finer, the faster alignment with respect to current chip-to-wafer bonding techniques. Yes, this is a long journey ahead. We are doing research pipelines to build the next generation of technologies to bring logic and technology and packaging much, much more closer together. Okay, let's step back. What am I trying to do? What are we trying to do? Our goal is creating the impactful technology pipeline along with the partners. For last 10 years, DTCO has served really, really well. And it has actually serving it at this point as we see 18A and 14A with our EDA ecosystems. However, when we are in the era of AI, where we are facing is workload-specific compute, system-aware technology optimization is needed. It's not only the design, you've got to understand the system. We cannot do it alone. Even the early R&D stage, we need to work with our system partners to bring our silicon and packaging technology together to define what are the pipelines, actually, breakthrough pipelines we gotta deliver. And that's what we really wanted to do. I start the journey of silicon and packaging separate, but you know that's no longer true. Now, actually, 3D IC is bring them together much, much more closer. For me, I dare to say that we actually not just doing the silicon packaging integration, we gotta do silicon packaging co-innovation together in order to go to next era. And Navid, who will speak next, will talk about the advanced packaging. And advanced packaging has been really playing a key role in the 3D IC and for the next journey of the AI compute. And I'm truly believing in this actually partnership that we need to work together with for early technology development with the partners. In short, the summary, 18A world first technology with the ribbon fed and power BIA has started risk production, as we actually shared throughout the morning and throughout the afternoon. In this forum, we announced a competitive Intel 14A technologies. For wide range of the market, we would like to serve wide range of the market. With the 14A, 18A base die technology can enable competitive 3D IC space of the solutions. We'd like to work with you on this space. The journey just began, and we need to continue. We are building strong technical pipelines to go beyond 14A, as well as actually silicon and packaging co-integration. I truly appreciate your attention. Thank you so much.